We're now going to talk about conditional probability. Sometimes the knowledge that one event has occurred changes the probability that another event will occur. So in that case, we don't have independence. For example, the estimate of a probability of being in a car accident increases if you know that it is raining or if it's snowing outside. So precipitation changes the probability. If you don't know what the weather is, you have a certain idea as to what the probability of a car accident is. If you now know that there's precipitation, that increases the probability of an accident. If you know there isn't precipitation, that decreases the probability of being in an accident. Several other situations, or one other situation is listed there. One that you might be aware of is the probability that you have of taking a retake in a class is a certain amount. You know that you might want to take a retake in a particular class. Maybe let's say it's 20%, but then you take the test and that changes your probability. You had a poor feeling about the test, so the probability that you're going to take a retake goes up. Or likewise, if you had a really good feeling, the probability will then go down. But then you get the test back, and then that changes your probabilities again. So the probability of you taking a retake after you get the test back and you see it's an A goes way down. So maybe it's normally at 20%, now it's at 4%. If you get a poor grade on the test, your probability of taking a retake goes way up. So that's kind of an example of what conditional probability is. Probabilities in the form of A/B are called conditional probabilities, and it's pronounced the probability of A occurring given that B has already occurred. So we will just read this, the probability of A given B. That means A is what we're trying to find the probability of, but we already know B happened. So we're going to take this data about the Titanic. This is actual real life data. And we're going to express this in a two-way table, which is a way to summarize the relationship between two variables that are just categorical. It's not like you are finding a mean or anything like that of these things. It's just we're counting basically. So we have surviving and dying, male and female, and then we total each of these up in the bottom. So down here where my mouse is, this would be the total males, this would be the total females, and then this would be the total of everybody. This is the total surviving, this is the total dying. And so we were given that there were 367 out of the 1,731 males surviving. We know that overall 711 people survived. We know that there were 2,201 people on the Titanic. So after that, we basically can just do some subtractions. So 711 minus 367 gives me the amount of surviving females. 2201 minus 1731 is 470 470 total females. And then we can just subtract up these columns. So we know that there were 1,364 dead males, 126 dead females, and 1,490 dead people. Overall distribution for gender is called the marginal distribution of gender, and the distribution for a specific gender category is called a conditional distribution. So they give examples there, and you can read those. Now what we're going to do is a bunch of problems dealing with this chart. So the probability that someone survived, all we do is we take the total survivors, which is 711, and we divide that by the total amount of people, that's 2201. The probability that somebody is male, that's 1731 divided by 2201. Probability that somebody is female and survived, so that means we take the female and survived, which is 344, and divide it by 2201. Now we're going to take the probability that you are a female or you survived. And so what we're going to do is we can do this in a couple different ways. We can do this with basic probability. So we can do probability of female plus probability of surviving, and then subtract the probability of being a female who survived. So we could just add all those up and then subtract the 344. Or what we could do is we could take the probability of surviving, which is 711 over 2201. And then all we have to do is add the females who died, which is 126 over 2201. And the reason all we have to do is add the females that died is that's just taking into account these additional females that weren't counted in our survival. So we end up with 837 over 2201. There are a variety of different ways you can count those. Letter E, probability of surviving given that you're female. It's the probability of surviving given that you're female. If we take a look at this, we're given females, so that means we're only looking at this column. So probability of surviving is 344. Probability of being a female is 470. So, well, probability of surviving and being female, because all we're doing was looking at that column. Probability of being a male given that you survived. So in this case, we're going to look only at this row. So we're going to look at given survival. So that means 711 is our denominator. Let's look at only the males in that row, and that's 367. Probability of dying given that you're female. So given that you're female, we are back in this column, the middle female column. So we have 470 as our denominator, and there were 126 dead females. Probability of female given died. So let's take a look at given died. So that means 1490. So we're looking at the middle row again. There were 126 females who died. Then probability of female given survived. So we're going to look just at the survival row. So that's 711 is our total. And then the probability of being a female in that row is 344. So now there are a lot of connections that we can make. Notice that both G and H have the exact same numerator. So the probability of dying given that you're female and the probability of female given that you died, those are different probabilities, but we're still looking at the same thing in the numerator, which is the probability of both of them happening. So that 126 is in the numerator of both G and H cases. If we take a look at the two probabilities F and I, probability of male and surviving, or male given survived, probability of female given survived. If we look at 367 over 711 plus 344 over 711, that adds up to 1. So if you add those two together, you get all of the survivors, because there were only 2 cases where there were survivors, and this means that it's a valid assignment of probability since there were only 2 genders in this case. And then we look at, I guess that's all we really need to know based on those 4 things down there. So let E and F be 2 events. The conditional probability of event E, given that event F has occurred, is the probability of E given F. That's our notation for it. That's going to be equal to the probability of E and F divided by the probability of F. So that's exactly what we did in those problems. We looked at the probability that something was of the given information. So, for example, in part I, we were given that there were 711 survivors. So we're given the survival. And then we want to find the probability of both. So that's the probability of being female and surviving, which was 344 on our chart. So that's kind of what the definition and how we're going to calculate that sort of thing. Following table shows the relationship between grade and driving status of Waubonsee Valley students. This is not actually true, but it very well could be. If you randomly selected a Waubonsee Valley student, what is the probability that he or she is a freshman? So we probably want to total these things up. So if we total these up, we have 27% freshman, 25% sophomore, 25% junior, 23% senior. And then if we add together all of the no driver's license people, we have 46 plus 21, and 46 plus 21 is 57%, I'm pretty sure. So that's 67%. Uh, that's not very good mathematics in your head. So that means that we better have 33% of people having a license, or else this is not going to work. And that's exactly what happens. What's the probability that this person is a freshman? We already calculated. If we randomly selected it, we will have a 27% likelihood of it being a freshman. What's the probability that he or she has a driver's license? 33%. What's the probability that he or she is a senior and has a driver's license? So if we are looking at probability of being a senior and having a driver's license, that's the probability of being a senior and having a driver's license. And so we're going to look, and that's just 0.16, because that's just this this cell on the table. What's the probability that a senior has a driver's license? So this is a little bit different question. This is the probability that we have a driver's license given that we are a senior. So what is the probability that a senior has a driver's license? So this is, we're given senior status. So that means that we have 0.23 in the denominator, and we're looking at the driver's license people, 0.16. So that's going to be 16 over 23. I'm just changing the decimals and multiplying the top and bottom by 100. I'm not going to get a decimal equivalent for that or rounded or anything. A legal driver is a senior. So that's the probability of being a senior given that you have a driver's license. So 0.33 is the denominator, 0.16 is the numerator. So that's 16 over 33. Notice that these two are not the same. So that's pretty important. What's the probability that a person has a driver's license or is a senior? So that's the probability of driver's license or senior status. So we can do that again in a variety of different ways. We can say that the probability of being a senior is 0.23 plus the probability of having a driver's license is 0.33, and subtract the probability of both, which is 0.16. So that would be 0.4. We also could do that by looking at cells on the table. So if we went up, we could say probability of having a license is 0.33, and then all we're going to do is just add together the additional seniors that don't have a license. So if I add those two together, I get 0.4 as well. General multiplication rule and independence. So when we were learning in our introduction to probability, we learned a rule for finding the probability of A given A and B when they're independent. We just multiply the two probabilities together. But now that we understand conditional probability, we can use the general multiplication rule, which means that if we want the probability of A and B, that's the probability of A times the probability of B, given that we know A already happened. Or likewise, we could say the probability of B times the probability of A, given that B already happened. So those two would be ways that we could find the probability of A and B. So that's the general multiplication rule. This comes directly from the conditional probability formula, since we know that the probability of A given B is equal to the probability of A divided by the probability of both. So that's the probability of A and B divided by the probability of what was given, which is B. All I have to do is multiply this probability over to the other side, and then we end up with the equivalence of those two things, or likewise the equivalence of those two things, depending on which one we were finding. What's the probability of drawing two aces in a row from a deck without replacement? So that is the probability of drawing an ace, which, since we know there's 4 out of 52 that are aces, then that's the probability of A. Then the probability of B is the second ace, so that's 3 out of 51. The reason why we know that it's 3 out of 51 is we have the probability of um, that second ace. We have to get rid of one of the aces from the deck since we already drew it in the first case. So this one is the probability of B given A. So since we already know that one of those aces has been taken away, then we end up with 3 out of 51. So 4 out of 52 is 1/13th, and 3 out of 51 is 1/17th. So that's the same thing as 1/13th times 1/17th if I wanted to reduce it. So that's 1 out of 221. My fault. 1 out of 221 for that one. And then we could have left it as an unreduced fraction if we wanted. So I'll leave it as 12 out of 2652, just to make sure that in case we have any confusion, I'll show you what the unreduced fraction is as well. Suppose that 23% of Wabansie Valley students are seniors and that 65% of seniors take a math class. What's the probability that a randomly selected Wabansie Valley student is a senior and is taking a math class? So I know that the probability, it looks like in this case, 65% of seniors are taking a math class. So we know that the probability of taking a math class given you are a senior is 0.65. We know that the probability of being a senior is 0.23. Now what I have to do is just kind of make sure that I'm using the formulas properly. So probability of taking a math class given you're a senior is the same thing as the probability of taking a math class and being a senior divided by the probability of the given information, which is the probability of being a senior. So if I want to find the probability of being a senior and taking a math class, so that's math and senior, that's going to be the probability of math given senior times the probability of being a senior. So that's 0.65 times 0.23. So if I have 0.65 times 0.23, that ends up being 0.1495. Suppose there are 12 girls on a softball team. 6 are freshmen, 4 are sophomores, and 2 are juniors. 2 players selected at random. What is the probability that they are both juniors? So that's the probability of junior and junior. So that's 2/12 times 1/11. The reason I know that is because the probability of being a junior on the second selection is going to be different because we have events that are not independent. So that's 1/66th if I multiply those together, or 2 over 132. What's the probability that neither is a junior? So the probability of not junior and not junior. So that is 10/12 times 9/11, because if neither one is a junior, then there were 10 non-juniors in the first case, and then after we take one of the non-juniors away, we're down to 9 non-juniors. So that's going to be 99 out of 132, which I can reduce if I really wanted to. 5/6 times 9/11. So that would be 45 over 66. Part C, probability that at least one is a junior. So remember that we've already calculated at least one problems. So at least one is 1 minus the probability of none. So that's 1 minus 45 over 66. So that's 21/66. And then probability that they are of the same grade. So that's the probability of both being freshmen plus the probability of both being sophomores plus the probability of both being juniors. So if I look at this, I already know that the probability of both being a junior is 2 out of 132, or 1 out of 66. The probability of both being a freshman would be 4/12 times 3/11. And the probability of both being sophomores, oh, oops, I put that with the freshmen, and I should have put that with the sophomores. So the probability of both being freshmen are 6/11 times 5/10. No, 6/12 times 5/11. Hopefully you're writing in pencil. So we end up with 30 over 132 plus 12 over 132 plus 2 over 132. So that's 44 over 132, which is the same thing as 1/3. Reminder, when you're sampling without replacement, successive selections are not independent, and you have to use the general addition rule, or the general multiplication rule, which is the probability of A times the probability of B given A, if we want to find the probability of A and B.